This conference will now be recorded.
Lovely, thank you. Thanks, Sarah. It was something that came up recently. I did a presentation to the PWI a few weeks back, but it was really reflecting back on what happened just over 20 years ago, and hard to believe that Hatfield was more than 20 years ago now. But really, a few things there as an introduction. A broken rail. This was broken rail. The left-hand one at the beginning of the picture there was what broke first. The rest of it broke up as part of the derailment. But a few pictures there on the slides, hopefully. The middle one, that was the broken rail, we believe, at the south end of it. In the bottom left, there's the pictures there showing the derailment site itself. You can see on the downfast in that ringed picture, that's where the rail broke initially. The train derailed, spread out across the slow lines and collided with a number of OLE stanchions and really ripped the train apart. Unfortunately, that's where the fatalities occurred in the buffet car, the service vehicle, which rolled over and struck that. So yes, somewhat reflection there that rail management still continues to be an important thing, and things we perhaps learnt from there, but making sure some of those things we still remember. So as a bit of an introduction, it's something that came up recently. So things, if you look at long-term history, and I always show this graph as it's generally a sort of good news picture, you can see broken rails there. We used to average about 750 breaks a year. We had Hatfield in 2000. And a lot of effort, a lot of activity, a lot of innovation development was brought in then really to look at reducing the numbers of broken rails. And that's been generally a big success story if you look at the last 20 years. But if you look at the last 5 or 10 years, things have pretty much plateaued. We're around about 100 breaks a year now. But some of the challenges now, that's perhaps still 100 too many. And what can we do further? So that's what I was going to touch on today with some of the things we can try and do to improve on that. Some of the activities that are going you may not have seen or heard about. So a bit of a whistle-stop tour through things, a bit about our problems that we currently have, what causes our difficulties, but also some of the things that might help solve these in the future. I won't go through the whole of this in detail. It's the old picture there from the last 20 years. And what I tried to do was add everything I could think of that had, apologies, I've got a transition in there I didn't really want. Yes, just try to throw a few things in there which were sort of things that contributed to those reduction in broken rails. And I'm certainly not going to go through them all today, but it gives a view there. It wasn't a simple thing, it wasn't one thing, it was a whole range of different activities that all contributed together to improve that from our 952 broken rails down to 107 last year. So yes, not an easy win, no quick fix, but a lot of activity there, a lot of work to do that. And some of the challenges now, to get those numbers down further, as I said earlier. I think I've coupled with that some of the key points. I think most of it has been around some of the improvement in monitoring and inspection, and certainly understanding why things break, understanding the root cause, often key if you're going to fix it, and certainly if you're going to prevent it happening again, making sure we understand why it happened. We tend to be very good in fixing the symptoms that we see immediately, but perhaps less good at fixing the underlying causes. So we're quite good at cutting in a closure rail and removing a defect, but do we really understand what caused that defect at that location? And are there other factors? So I'm going to talk a bit about some of the things we're trying to do to improve that. As I said earlier, no or very few quick fixes, and unfortunately no magic wands to make that happen. So the challenge is now that the quick wins we've already had, we've already achieved those, we've already made those improvements, and further reductions are becoming increasingly more difficult to realise. So certainly a challenge going forward of how do we improve further. Because a lot of our corporate memory doesn't go back to 20 years. People are expecting things to be improving year on year. And if you look at the last few years, that's something that perhaps hasn't happened as quickly as we would like. or we've seen a relative plateau. I'll go back to this slide again, and particularly the picture in the middle there. Something there, big transverse defect from RCF in the head of the rail. That resulted in the rail break, the initial rail break and the derailment. Something you'd think now we've largely eliminated. But I was looking through sort of recent records. Some of the things, this is one from January 2019. Broken rail, initial break, and again, nearly full head defect there in the head of the rail, caused by a surface RCF. And then a second break, because we continued to run trains over that before it was picked up, from a much smaller defect, also RCF related in the vicinity. But you can see there, once you've got a cantilevered rail from the first break, the risk of a secondary break increases dramatically. And even a small defect that may be in that vicinity can result in a secondary broken rail. We were very fortunate in this location. We didn't lose a longer length of rail and potentially a derailment that could have happened. So yes, it's something there, and a close up there, that's the secondary break. You can just see the small RCF cracks, nothing particularly large in that situation, but enough to cause a weak point that the cantilever rail failed. And following on this theme, it's something, just to show which two breaks occurred, the break in the middle of the bed first of all, and then another one from December 2019, and very much a common theme, similar picture. This one not caused by surface damage, but a true Tashaval, an older rail that's grown from an internal defect in the rail steel. But again, a very large defect that grew, that broke, and that was the initial break. And then secondary break from a much smaller defect, perhaps one that on its own we wouldn't be overly concerned about, but coupled together with an unsupported length of rail, the risk of a secondary break, then the piece of rail coming out. And again, fortuitous that we didn't have a derailment in that situation. But a common theme there with a number of them. It was just some examples. These are ones I would certainly expect to be able to prevent through adequate inspection. And the final one I was going to show more recent, this was this year, 12th of May. A failure there on the up quarry line between Red Hill and Quarry Tunnel. A few things we're still investigating here a bit more further. This was a premium rail steel, an HP grade rail, only 5 years old, a very large transverse defect from rolling contact fatigue in the head of the rail. Fortunately, this was just resulted in a single break. We didn't end up with a secondary break, but certainly the risk is high there because the nature of RCF and its the likelihood of similar defects in the vicinity greatly increases the chances of the secondary failure. So some fortunate ones there where we didn't end up with a derailment, but in other situations potentially it could have been a lot more serious incident. So it's one of the challenges. Although we've reduced broken rail numbers, we've not eliminated them, and the risk still is out there. And that's something certainly from my point of view is concerned that this sort of defect, particularly with transverse defects in the head, should be something we are able to prevent through inspection. And so a little bit more, but that's likely to be still subject to the inquiry. But really understanding, did we find a defect? Did we act on it appropriately? Even if the inspection finds it, if we don't carry out the right actions, potentially we're no better off. We've got to follow through and make sure actions are taken to either remove that or protect it. Next one is an example from the previous break. Some new data. It's our eddy current data, and at the top of the screen these are plots. So the left rail at the top, right rail on the bottom. And this is the RCF back in October 18 with some small patches of it starting to form. You can see a year later in November 2019, much more extensive RCF. The density and the size of the green bars there represent the depth. So you can see it's increased there. So it's stuff we perhaps knew. We knew things were deteriorating from 18 to 2019. But the challenge, I think, with a lot of these is making sure we make best use of all the available information. We tend to look at lots of different things, but in isolation, perhaps not always foreseeing some of these problems. So something perhaps just through the eddy current data we should have seen coming. The RCF was getting worse. it was getting more extensive in the curve and getting more, or certainly more severe quite quickly. That's a big increase in damage for only a year. So some of the things I'm going to talk about, a bit about using this data more effectively and some of the challenges that brings. A little bit about the cause. So if you're going to try and tackle certainly reducing numbers, but it's one thing I've been pushing, that it's not just the numbers, it's making sure we understand the types of break, because the risks they present can be significantly different. So just as a flavour there, you can see over the last 5 years, from 2013 to 18, rail foot corrosion or rail foot failures, these are small transverse defects, and I'll show a few examples, are by far our dominant cause of broken rails. They account for about 40 to 50% of all our breaks now, partly because we've done a lot to reduce the other types. So some of our previous weld failures, which used to run to 30% a year, that's now down to about 10 to 15%. And even there, they're mainly old welds. So a lot of activities there to improve it. But what it does mean, certainly from a type of break and cause, that rail foot transverse defects or pitting, whatever you want to call it, is become an increasingly big problem. Perhaps not in total numbers, the numbers have been pretty much the same, but as a percentage contribution to the overall number of breaks, a very sizable target there, and something that particularly tends to affect our higher speed, higher tonnage lines. Couple of examples of this type of failure, some very obvious. This is a site, we had 2 broken rails at this location, both of them foot failures. And in both situations there, really, because we're asking the rail to do too much. If the rail is effectively a beam in bending, and ideally it's supported by the sleepers rather than having the sleepers hung from it. So a transition area on a structure, but a common problem area where we ended up with 2 broken rails at this location in older rail, but with a high fatigue damage because of large bending forces over a long period of time. But some of them, perhaps could we find it by UT? A lot of work we do to try and do that. So for example here, the rail, you can see a small crack in the foot of the rail. This is actually quite a large defect compared with some of them that fail. But even the opportunity to find that, will it be in the middle of the web, directly under the web in the middle of the foot, where we might be able to get an ultrasonic signal to it? Can we distinguish that from general noise from the rail foot because of a degree of corrosion, general corrosion, some surface irregularities? They all produce ultrasonic signals, but it's something we spent a couple of years looking at, unfortunately not with any positive confirmation of this type of defect, and perhaps understanding more about how quickly does it grow. Is it a sort of single event? Is it a few events? But certainly you can see from the size, it's quite a challenge to find something that small in the foot of the rail. It's a long way from your ultrasonics at the top of the rail, and you get a lot of noise back from the surface, general surface irregularities. Another example here, this one from the West Coast main line, typical foot failure, straight over a sleeper. Fortunately, all stays lined up on the sleeper, which is good. But when we looked at this one, again, a lot of voiding. You can see in the picture around the sleeper, the edges of the sleeper very badly worn. So it's clearly been moving in the ballast for quite a time. And what's not shown in this picture, again, this is a transition to a structure, but a common theme where we've got poor support conditions. This one though, the broken rail, there's very little to see, and that's the foot where it failed. That's the point it initiated the defect. Yes, perhaps there's a little bit of a pick just to the left of the arrow, but certainly not something there where ultrasonics is going to be a technique where we can use to find them. We're not going to find something like that. That's perhaps an extreme example, but generally this is a very small defect we're trying to locate and manage in the foot of the rail. So I'll be looking at what else potentially we can do if we can't solve this by straightforward inspection. Are there other things? And this is a geometry trace from the same break, the previous slide. The only thing, a real note there, it's a pretty good bit of track, good track quality, nice straight track, except for a dip angle. Now, if that dip angle had been an IRJ, perhaps expected, the joint is a little bit softer, but this isn't. This is a bit of plain line and quite a sizable dip angle there for a piece of plain line, and perhaps a clue there that this is a problem location, and where that coincides with older rail, it's been there a long time, then we have a higher risk of foot failures. You can see on the dip angle trace, there's nothing else around it. It's not riddled with this type of fault. It's quite a localized effect, and that's quite common on a lot of main lines, and perhaps not a problem in younger rail, but when we're starting to run higher cumulative tonnages, this rail was an older rail, perhaps something between 1,000 and 1,500 million gross tons. So American billion, 1.5 billion tons over it, but generally in reasonably good condition, except for this local spot with a dip angle. So one of the challenges is to look at what other information we have that may give us a clue to these locations and the risks they present. Just an example picture a colleague sent to me. Really an example of, apologies, I've got a bit of a lag on my mouse, so apologies on that one. Yes, it's sort of quite a striking picture, but it shows you a modern vehicle, modern rail, conical wheel profile on a crowned rail, and the very small contact patch. So certainly some of the things now, and a lot of our modern vehicles run very consistently, always on the same piece of the rail. They're not moving around or hunting as much, but certainly quite a challenge for a materials point of view. The contact stresses at those points, perhaps around 500 newtons per millimetre squared, something approaching the yield strength of the material, even as a static load. When you start to increase that because of roughness, dynamic loading, the forces increase quite dramatically. So quite a challenge there, and just a striking picture I was sent showing that the very small contact area, about the size of a 5p piece, a coned wheel on a profile or a crowned rail in that situation. But yes, asking a lot of the materials in that situation, particularly when we repeatedly run over the same location. RCF, it's not gone away, and in general, looking at data, it is still increasing. The volumes of severe RCF are still increasing, not particularly quickly, but they are slowly creeping up. This is an example of a rail. This is surface cracking you can see in the top left picture, highlighted with magnetic particle testing. The red line indicates there is the crack growth under the surface, and this is the sample actually broken open at the point of position 2. And you can see the transverse defect that started at the surface, propagated some way down into the rail to about 5 or 6 millimeters deep, then branched and turned into a transverse defect, which this one fortunately didn't result in a broken rail. This sample we broke open, but it shows the extent of growth of cracking that can occur from something that perhaps on the surface doesn't look quite so serious, and that's one of the sort of challenges. But certainly RCF's not something that's gone away. It's still growing in smaller volumes when you look at it year on year, and it's something certainly from my sort of radar and headline, we need to make sure this doesn't creep up on us, that we end up with an unsustainable amount of re-railing, and similar, we find more effective ways of controlling it. The next slide is just an example one I put up. Traditionally, we've looked at using visual inspection to try and locate RCF, focused primarily in curves, focused often on the high rail, but it doesn't always occur in those locations. We often get other sorts of damage. The top left picture, very isolated but associated with a weld. Small change in the profile, perhaps a change in the metallurgy locally at the weld, but a very short patch of that, of RCF, which if left untreated will go on to cause a defective rail and in due course potentially a broken rail. Picture on the right, low rail damage, low rail of an overcanted curve used by heavy freight, and you can see the physical extrusion off the surface that spread towards the field side of the rail, and trying to measure those cracks. How long are they? What's the surface length? How deep is that? Is quite a challenge in that situation. And the bottom left picture I've included really not cracks, grinding marks, residual grinding marks left from where the rail has been reprofiled, but often difficult, particularly where they coincide with the RCF. Very difficult then to pick any cracking in or to measure anything. So it's one of the challenges of what we could try and do to be more effective at finding the RCF, how we could manage it better. One of the things we looked at, we've been working with Sperry, who've been providing our ultrasonic test equipment on our UTU vehicles. There's some development there we put out to them through a tender eventually that resulted in looking at better ways of surface crack detection. Sperry was successful with the tender effectively and produced this piece of equipment. Looks a lot like their standard roller search unit, which is used for ultrasonic testing. These are a couple of examples with and without the tyre of their new eddy current equipment. It can be fitted effectively in exactly the same way to our test vehicles. So something we put in there, this is the next generation. This is now fitted to our trains from September this year. We had a period where we weren't recording RCF because of the COVID problems and need to socially distance on the trains, and to avoid perhaps risk of losing ultrasonic testing, we stopped doing eddy current testing from April through to September. In the meantime, though, we took the opportunity to upgrade the equipment, and the main change is the 10 probes which are close to the rail are time now, which constantly pressurised to maintain the correct pressure, so you get the right footprint, you avoid any leakage and punctures. You can also detect if there's any problems. So something we think will have a significant improvement in the quality of the data and repeatability of the data, as well as reliability of the equipment, so less lost testing. So that's now fitted to our vehicles and it's been rolled out on 6th September. Previous systems, we've been collecting data and have been looking at this, and then it's one of the challenges, certainly I haven't perhaps foreseen as much as we had, was to understand what did we do with the data. Data is fantastic, but only really useful if we can turn it into something that people on the ground can understand, can process, can act on. If you do nothing with the data, then it is of little benefit. So perhaps one of the challenges the eddy current has brought us. So we made some changes to our rail defect management system, and we produce a lot of data from it. And an example here, this is a section of track. It's effectively every yard of track where there's RCF detected, and the system has the 10 probes, and that is measuring the depth of the RCF from the gauge corner to the field side of the rail. That's through the channels DC0 to DC9. They're always labelled that way round. And then under column G, you've got the deepest crack detected within that 1 yard. And as a bit of an example, the data in this situation, if you look at the top line of that data, you can see some cracking there under DC0, DC1, DC2. That corresponds to the probes which are mounted on the rail. So DC0 on the gauge side, DC9 on the field side. And if you correlate that to a transverse section through the rail, you can see the cracking there perhaps a bit deeper, but somewhere a region sort of 15 mil from the gauge corner, 20 mil at the deepest point. Perhaps not surprising, that's what we perhaps understand with RCF, but how do we use this data? Because you potentially just presented with a huge spreadsheet of numbers. So we've been doing some work on trying to visualize this data. These are some early examples of something I've put together, taking different parts of different systems. So I've got a track layout from LADS, curvature plot. I've got some rail age information, and then on the bottom I've plotted the eddy current data, which is showing the depth of crack on the left rail at the top half and the right rail at the bottom. And it maps as you would expect. You can see cracking on the high rail of the curves. So where the curves reverse, the RCF changes. What you also see, and perhaps is the cracking that's also on the low rail, perhaps because of lower speed freight traffic on these particular routes. So it's not only the higher speed passenger traffic affecting the high rail, but we also get corresponding damage. Some of the other things we're starting to see now is it may not be in the main body of the curve. It can often be worse in the transitions. So where our perhaps cant and curvature aren't as well aligned, we get to a certain level of cant deficiency, which is perhaps too little to cause the vehicle to steer better, and more than we'd have in straight track. We get to a sort of worst case example in some of the transitions where we haven't maxed the cant deficiency, which will tend to reduce RCF damage because of the effectively forcing the vehicle to steer more effectively. So it's something we're trying to learn and do more. And how do we get stuff for this information? It's very useful, this looking at an individual site, but how do we look at this in more detail? How do we program this data? And I think that's one of the challenges we perhaps didn't see. Here's some examples of perhaps why it's difficult. These are the eddy current plots. The blue stuff is the left rail, the green stuff is the right rail, and these are plots from top to bottom, old to new. And one of the things you can see quite significantly, this run in February, for whatever reason, at this location in the centre of the picture, we've got a significant offset. And if you just look at one site, for instance, there's the site here, it disappears in February. It hasn't actually disappeared, it's just moved up the track a bit. So making sure we've got common location. And one of the other things we must be careful of, this April run here, the left channel ultrasonic, eddy current failed. So there was no results recorded. And because it effectively only reports where it thinks there's RCF, you have to be very careful that you understand whether it's been tested effectively, or potentially you think there's no RCF when actually it's just not being tested. But that's some of the challenges we've been having at the moment, is how to get this positional accuracy more consistent and not have this variation in mileage, which effectively can appear to see a site disappear or reappear, when in actual fact we've got to find a way of doing this. And that's something, hopefully now the trials, we're using the real-time positioning system under a trial on U2U3 at the moment. That's currently going through some testing, but making better use of that and making use of this data more effectively, it's key that we get this tied up and aligned properly on run. If you want to start to look at sort of automated deterioration rates, then you need to be able to make sure your data is properly aligned longitudinally or positionally. A couple of other challenges with data. It's something where we're looking at with the enhanced decision support tool, the infrastructure investment program. And we've been looking at data from other sources, but it's their very big focus. This is a rail profile or Sidewear. So we've got equipment on the U2U which measures the rail wear, both vertical in the centre of the rail and 14 mil below the crown for Sidewear. And you can see just quickly on here that we're struggling making sure left and right rail is consistent. So we've got some of the runs, these different colours are all different runs on different dates. And ideally we would then see it changing from run to run as Sidewear increased. But you can see, for instance, the blue bit there, that's very clear in the top trace. That should have been on the other rail. But for whatever reason, on one of the runs, left and right rail were reversed. And where that happens a few times, it starts to then give you quite misleading information. So I'm trying to say it's key that we get data accurately positioned, accurately reported, if we're to make better use of some of the system. People get to trust this information and to rely on it as a means of identifying problems or at-risk locations. So yes, some challenges there with how we make sure that's always consistent, but very clear in the Sidewear where we have reversal from left and right. Some of the bits we're still working through, and the new machine is currently doing trials in the country, the new Linsinger. That's currently undertaking work, finishing off vehicle acceptance side of things, but one of the ways perhaps we can more effectively treat rolling contact fatigue, once cracks have got to a certain depth, we're either faced with continuous testing time before we end up re-railing, but potentially some opportunities here. Some of the new things we might be able to do to reduce some of the surface damage and actually remove it. So we've had some successes where we've been able to mill, remove the cracking up to 5 millimeters deep, effectively produced a rail then free of RCF cracks with a very good profile, and then effectively, rather than changing the rail just because we've got some surface cracking in the top 5 millimeters. When you look at the cost of re-railing, it's important we get a full life out of the rail. We're not changing rail just because a small amount of damage near the surface. So some of the challenges, how we get enough resource, how we plan that effectively and efficiently. They're not the cheap machines to run, they're expensive to buy, and getting the right treatment in the right locations at the right time will become key in making these successful. Some of the other bits we've been doing to try and improve things. First stage, we've been doing a widespread conversion of equipment to move from our old A-scan technology, which was a Sperry walking stick, and a third-party flaw detector that we used on the top, which displayed things as an A-scan. You'd need to watch the screen to identify stuff, but to move to something with BScan capability. BScan is different presenting the data. It's the same information, but provides a pictorial view of the defect in a two-dimensional picture within the rail. So it works out what the position is, the angle, the depth, and the size. Currently, one of our challenges will be to move to using the BScan. We currently use A-scan technology, so we're reliant on looking at a screen, seeing how high a amplitude or a reading is, or what position it is on the screen, and then estimating its depth based on a measurement or lookup table. Effectively, if we can get to BScan, all of that information is provided. It will match better with what the train produces, but it does give the opportunity to carry out sizing of defects more easily without the need to do additional things like hand testing that we currently do to measure the depth of something. We could do that all from BScan, but it's certainly a challenge going forward, how we get people trained, how we get people confident with it and skilled with the right resources that they can use that. It is a different way. It's the same data. It's a different way of looking at it, but it is a challenge, particularly where we've got to get through union consultation and make sure we bring operators with us so that they understand what they're seeing and they can report it. The BScan is also an advantage. We've got an auditable recorded record of all testing. So you can go back and view the results on the screen. You effectively see a few meters of the test all the time on the screen, but it's also recorded so you can go back and revisit that afterwards. Provides a positive record of something being tested. So there are some big benefits. It's a question now of realizing we're currently using the equipment in the original A-scan mode, but moving to a B-scan is something we're looking to try and do and roll out to improve both the audit trail from testing, from pedestrian testing, but also better ways there to actually record the data and to be confident we've not missed something because it's something that flashed by on the screen. A couple of other examples of real sort of technology where we're trying to bring things in and some of the improvements. This is a bit more on the ultrasonic side of things. We currently have the RSU, which is fitted in our walking example here. A UX9 as it's called, it's got 9 probes in it. That's where the 9 comes from. These are the bits that fit inside the tyre, and we have an array of 9 probes there to try and detect the defects either in the head web or foot of the rail or horizontal defects in between. Some of the things we've been looking at are the potential, which Sperry currently are trialling in other countries. How can we go a bit faster? We're limited to a maximum of 60 kilometers an hour with our current equipment, but there are opportunities to move to faster testing speeds. How much of an advantage that will bring? How fast can we go with larger RSUs? Some of the other things we've been looking at are VSH, or vertical split head, what we perhaps call longitudinal vertical splitting. Something that, because it's along the length of the rail, difficult to detect with current ultrasonic transducers. So we're looking at the potential and just starting trials now, initially as a walk stick, to make sure we understand the defect. That's a small example. It's a big crack, but hasn't opened up as this point. But something there where the danger in the rail, it's a result of a derailment back in 2014 at the Vale of Glamorgan, where the low rail broke up because of a longitudinal split. The head effectively split in half, and a freight train derailed at that point. And then how we better perhaps test for that. Currently, we have sort of at-risk locations, we're looking for any telltale signs on the surface, or we're trying to scan it with a hand probe from the side of the rail. And if you can see that one's grown significantly, and effectively you lose the whole head of the rail, or certainly one side of the rail. So a serious defect there, and it in itself doesn't necessarily initially present anything significant to see with conventional ultrasonics until you start testing from the side. So one of the developments we're looking at currently, it's just starting doing some trials at the moment, is what they call a vertical split head or SideLooker from Sperry. It's a different arrangement of probe, and the probe bounces it off the fishing surfaces across the rail, potentially looking for something that lies within the head of the rail. So we're just doing work on the moment there as to how best we can use that initially as a pedestrian piece of equipment to screen rail, so we know whether there's anything in there as a quick way rather than having to hand test it, and also a potential to put it on a vehicle to run and perhaps understand how much rail is affected in some of our older rail steels. So yes, some bits there that Sperry have offered. We're looking at how we perhaps utilise those more effectively and benefit from using them. Can we fit on our vehicle? Some of the other things that have just been developed, they're doing their initial trials with some customers now. It's a high-speed RSU. It spins very fast, but it has cooling systems in it. So they put a big heat exchanger, and there's a fluid cooling system to keep it cool. Initial trials suggest that may be able to test at speeds certainly up to 60, if not 80 miles per hour. So potentially something to look at where we perhaps want to do more miles, less shifts, or perhaps something where we could test during the day in traffic without having to take up possession times at night to run a slower vehicle. Some of the other things we're trying to get to now, making sure we can link things like the crack depth. So at the moment we have our ultrasonics reported in one system, eddy current reported in a slightly different system, but they're both defects in the rail. The eddy current often a precursor or pre-warning of ultrasonic defects, but present them together. Let's synchronise them. They shouldn't be something that's two separate outputs. We ought to be looking at the two to give us better information. So one of the things we've got to challenge with Sperry is how do we synchronise this into a better BScan? So we've got eddy current against BScan, so we can get more information about the same rail. Some of the other things we're pushing to try and do is to perhaps use a vision system. This effectively uses the ultrasonics to take a snapshot of the rail at that particular point where a suspect is detected. One of the big advantages, potentially, welds and things can look like a suspect defect. By taking a picture, we can confirm that's a weld. So the example on the right, there's a picture of a thermic weld with a collar on it. The analyst doesn't send us out to go and verify and tell them it's a weld. They know at source, so perhaps help there in reducing the number of suspects. But I think we're looking at how we perhaps introduce this into our fleet, certainly going forward through the retendering exercises and similar as to what we get from a train-based inspection. But again, it's combination of data and linking them together is where it's key. The attractiveness of the Sperry system is that it is immediately linked because the ultrasonics is effectively what triggers the camera capture. So you know you are perfectly synchronized. That's a challenge when we've tried to do the same thing using Sperry ultrasonic data and then linking it with PLPR. You have to be very confident with your synchronization position. So quite a challenge there and quite a slow process to do. Whereas if it's perfectly synchronized and presented to the analyst at the same time, a bigger option there. Some of the other bits, not quite so sexy perhaps, but putting the same sort of technology on a dual rail system, something to test both rails at the same time, potentially with ultrasonics, eddy current, etc. on there, utilising the BScan type technology to be able to display it as two channels. Can either be used to record lengths of rail. We've been doing similar things with other bits of equipment from other suppliers like Cater. So it's really looking at what else can we do to improve perhaps pedestrian testing, make it more effective and more efficient. Some of our testing of S&C Can we combine multiple tests onto a single small trolley, which either can be pushed along or towed behind a powered trolley that we have? So some challenges there, how we bring that in. A couple of others we've been looking at as well. A lot of the time we're spending effort writing forms out, recording data manually, writing defect numbers, recording locational information. It's often a problem, and this is something Sperry have offered, potentially with link to their defect management system, but is the use of handheld technology, which effectively tells you where you need to test, then records the test, records your position, and you can then mark any features that you see during that testing, reference those. So something there that perhaps some challenges, and probably some of the bigger challenges, is how do we make this sort of technology talk to our existing legacy systems? So communicating with our RDMS so that defects are automatically loaded. We're not having to write a form out, take it back, give it to someone to then manually type into the system. Certainly trying to improve on things like the quality of data, how accurately we classify something, how accurately we report position. So some technology there that potentially offers some advantages in giving more information to the user on the ground, automatically determining location, recording any features that are seen, and allowing them to provide any comments, feedback that they would do normally, but largely done through a handheld without the need to do a lot of paper chasing, paper form filling. On the subject of sort of linking the data together, it's something I've been pushing to do. We can go looking for new data, but often it's data we already have. This is an example. This is our rail profile information that's currently measured by laser systems on our UTUs. I won't go through it all in detail, but the bits I've highlighted in red are effectively a measurement of the width of the head. And you can see at that location, we've got something that's 71.9, 72 wide, compared with the rail around it at 69.8. So it's not a heavily side-worn bit of rail, fairly reasonable condition, a bit of vertical wear, 4 or 5 millimeters of vertical wear, but this localized widening. It then got picked up by a UTU, and independently, a suspect was indicated from the UTU of a possible vertical longitudinal split. That is an image of it from the PLPR that we can see. You see the widening locally at that point. And when we got the ultrasonics out to confirm it, they were to mark up the extent of it, measure the severity of it, and a defect there, 1B defect, that we then ended up removing. But certainly something like that, where perhaps the first telltale signs were around the head starting to spread. And then potentially, by the time we then find it with ultrasonics, with our conventional ultrasonics, it can be quite late in the day. So ideally, we want to be finding these before we need to put a speed on, so we can plan their removal without affecting performance. So some of the challenges there, and that's why we're looking at not just perhaps ultrasonic data, but using multiple data sources, some of or most of which we already have, but making sure they're synchronized and aligned. And that's something we've been doing work with the infrastructure, intelligent infrastructure, the II program, to try and bring this forward so we have a better way. Some of the things we've been looking at, we still suffer problems in wet tunnels or local areas of corrosion, level crossings. This is an example, it's a broken rail, but huge amount lost on the foot, off the head of the rail at that point. So a loss of rail depth at this point, a very worn, flattened head profile. But again, a defect there that resulted in a broken rail. And making sure we understand that data, we identify that in sufficient time to plan its removal. It's not something that's happened instantly, but it's still a challenge to get that information. It's a manual measurement. It's not an easy test to do. And trying to do that through sort of dark tunnels, wet tunnels and things is quite difficult. Another example here where the rail, this one was picked up as a cracked rail, but virtually broken, or certainly broken by definition, but picked up by PLPR. But looking at it, we did pick it up originally. It was fractured along the foot, we had a minimum depth exceeded at one location. It was put in as RDMS as a 1-year defect. Unfortunately, that was dispensated out for a further 2 years to allow plans to re-rail it. Unfortunately, it broke in the meantime from that point. So it's one of the challenges I look at. Some of the actions, particularly where we've got something perhaps replace rail within 3 years, is what the standard says. We tend to look at that as replacing rail in 3 years rather than within 3 years, and a subtle difference between the two. But some of those actions, people look at the long time scale actions. Are they as severe? Are they as significant? And do we have the same risk? But if not acted on, it's something there. It's easy to extend it for another year, for instance, but potentially we run a risk then of having a broken rail, perhaps in a location in particular where we don't want to avoid that. So breaks in tunnels, that sort of thing, present a much higher risk. One of the things we've tried to bring in now, this is an output of the rail depth data. So while part of the ultrasonic testing, we measure the signal from the top of the rail to the foot and back. By measuring the time that takes, we can effectively measure the distance or the height of the rail. Now, these two plots look a bit strange. These are actually gall. So this is over a 22-yard length. And you can a bit more, yeah, 22 yards. You can see the gall on the sleepers. So everywhere the sleeper is, the foot of the rail is worn. That causes a reduction in the rail foot depth. This is to a level crossing. So that's effectively the signal you can see from the rail foot. So we know we've got gall, a significant amount of gall in that location. But if you look at the sort of wider data through a similar rail depth information, you can see very locally in the crossing, we've got some patches there where we've got a general loss of section, perhaps not the gall that we saw in the previous picture, but this example shows localized loss of section. That's effectively where the foot is missing and has effectively caused a reduction in the depth of the rail. So something that looks fine on the surface, but what's happening under the crossing, for instance. But again, something that the data is there from the UTUs, it's just making sure we can present that. How we flag it up is it's not the easiest thing. It's big data files because we have a signal every 3 to 5 millimeters the train runs. Most of which doesn't show us of anything of interest other than the depth of the rail, perhaps how much vertical wear we might have. But what we need to be able to do is drill down and identify these at-risk locations so we can go and either inspect them in more detail, but we know where to go and look, where to do something, or we take the data and act on it, where we've got a significant loss of foot section in this location. You can see the left and right rail. Left rail's clearly defective, right rail's starting to show a few in, but nothing like the severity that is on the other rail. So using this, the advantage, we have this UTU data everywhere where it runs. It's not something we have to go and test a spot location or a themed inspection or a manual test at one point. We've got the data everywhere the UTU runs. We don't have to be so cautious or so careful that we have to find these at-risk locations. And we're finding now, looking at the data, we're seeing problems where we have a bridge over the railway, particularly a main road bridge, and we get a lot of salt contamination and water coming from the structure above, causing localized corrosion. It's not something our current standards flag up. We flag up tunnels, level crossings, coastal areas subject to corrosion, but it's something that we've perhaps not seen until we've looked at the wider data. We can see we've got these localized problems where we've got a road over rail bridges. But again, data we already have, but certainly the challenges I see is how we turn that into useful information. A couple of other bits of technology out there at the moment in a sort of vein, the latest BScan. This is a slightly different kit. It doesn't use our conventional sort of pitch catch or pulse echo ultrasonics. It sends a longitudinal wave or range of waves along the rail and looks for any mode transformation rather than direct reflection. The big advantage is you can put it on the rail, it will look, and it really looks at the change in section. So it could be something where the foot tips are missing, or there's a general loss of section from the foot or from the web, which to an ultrasonic probe may be very little visible because it's not a sharp transverse thing to cause a reflection. So this is currently the next generation is out there now. It's being trialled on LNE to look at level crossings primarily as a screening tool. So it can carry out a non-destructive test without lifting the panels to see if there's any extent of corrosion, predict when they need to perhaps do a more detailed inspection, but also perhaps avoid lifting the panels, finding there's no rail and ending up with a speed restriction or chasing around for a new length of rail to put in a short period of time. So something to perhaps better target when we need to lift crossings, which crossings are particularly at risk, where we've got some difficulties. So that's just going through some trials, excuse me, at the moment. A couple of other bits going to include the Intelligent Infrastructure Project. You may have heard the II project or the DST, Decision Support Tool. They're currently gearing up to look at Work Package B, which is primarily looking at different sorts of data for rail management and bring them together so that we've got confidence of location, we've got accurately and if necessarily realigned data. We've seen some of the benefits already now with some people may have seen the site clip top tool, which looks to predict where we may have site clip top or where we're getting close to something that requires action and trying to make predictions of to when that problem will manifest itself. So getting the right data there, and that's some of the things they're looking at with rail depth, which is what I've just shown you from the UTU, Sidewear measurements from the systems on the UTU, looking at rail profile faults. Have we got problems where we've got localized head loss, we've got perhaps excessive side wear, eddy current RCF, rolling contact fatigue, bringing in the normal ultrasonic information, making sure we've got other key features. We know where our insulated rail joints are, things like that. We can better make use of that information if it's synchronized. Certainly where I've been looking at the dip angle as perhaps a precursor to some of our broken rails. Understanding what's caused that dip angle is key in that point, because if you look at a sort of setting a limit of 10 or 15 milliradians, a very small dip angle, you will pick up every insulated joint, most crossings, and similar in that trace. What we're looking for is that small dip angle, perhaps to act on it, but where it is in plain line. So it's not a joint, it's not a physical feature like a crossing nose, but using that information, but having that data to confirm what is causing that dip angle. So we're not having to look at hundreds of thousands of dips, small dips. We know which ones are caused in plain line, which greatly reduces the volume. If we start to link that with things like rail age and other in data, it potentially gives us a much better window and opportunity there to identify at-risk locations of foot failure. Perhaps something we can look to then replacing this older fatigue damaged rail before it finally fails. But understanding enough data there to be able to narrow down the dips to which ones we need to do something with and act on. So I'm hoping this will help with a lot of that information by presenting series of data we perhaps already have, but in a format that's showing deterioration, gives some prediction as to when problems are likely to occur. But key in that is aligning this data together. It's not just broken defective rails. A few may recognise the location, but a buckle this summer through the movable length of the switch, and some of the things I'm keen to do. Some of the research we're looking at is how better do we identify these at-risk locations? Can we do more to perhaps understand the conditions that may have led to this? And one of the things we're looking at, we've got some research work being done at the moment. So some work with the University of Southampton is currently underway. We're hoping to finish by March next year, of really looking at a model. What I'm keen to do is understand a lot of the things we hit in our hot weather management standard, mod 14, around disturbances and deficiencies. How much of those are critical? How much do other factors affect it? So is it all about SFT? Is it all about rail temperature? Is it about the alignment? Is there a geometry fault there previously that perhaps increases the risk of a buckle? Some things we don't always look at, but making sure we can effectively build a model and then look at the sensitivity and perhaps better understand what conditions perhaps are key, so we can better target those problems. Generally, it's okay, provided we have identified any deficiency or disturbance or loss of SFT or low SFT. but understanding which of those becomes more critical. And certainly the SFT itself is something key. And actually, we're doing this testing today as we speak now. They're out doing some measurements with new technology using some very clever time of flight technology with ultrasonics to look at potentially being able to measure the SFT from a rail condition without the need to perhaps unclip the rail or to cut the rail, to go into a site blind effectively and record it. It's something I've been looking at as almost a holy grail for a number of years, but we're still pursuing different technology. This is perhaps the latest one we're looking at with the potential there. They believe they've got now this new version of technology that potentially will be able to assess what the stress-free temperature at a particular location is, but certainly help with understanding whether it's something we do regularly, but certainly at key locations. So I'm keen to explore that in things like S&C, where we know perhaps there's a risk, but we've also got potentially a fixed point in the form of a crossing on long bearers where the stress may build up or pull against. So do we have the same SFT we think once we've installed it? Does it change after traffic? How fast does that change? That sort of thing. So things we can help, and that's out at the moment doing some work alongside the induction welder, which I'll show a couple of pictures on just to finish. This is the Mirage network rail combined machine, the latest guise of it. It looks a bit like a flash butt welder, but instead of using electrical resistance heating to heat the rail ends, effectively it clamps over the rail. It brings two disc-cut rail ends together, puts a force onto that, and then locally heats it using induction coils to heat the rail up to approximately 1500 degrees C. It takes about 3.5 minutes to reach that temperature. It then applies a constant force, and that effectively forges the ends together. The uncut ends, any oxidation or anything else, is then extruded out the outside, and the rail, much as a thermic weld is stripped, or a flash butt weld is stripped in virtually the same way. But some big advantages with it: you're able to much better control the heat input. And effectively, it's like switching on your cooker. You dial in the numbers you want and the time. You can hold the temperature. You can use that quite effectively. It's quite quick, and it uses a vastly lower power than you would require for a flash butt welder. It's not a small machine, but you've got to be able to push two rails together and overcome the forging forces, and it has some challenges in that it does consume about 25 millimeters of material, so you need to be careful where you're doing rail welding and managing stressing. That's what's being done today at Grange Sidings. They're currently welding up, but at the same time I'm hoping that the technology from Sheffield are out on site with them will be able to measure rail stress, and we get both effective welds that we can potentially re-stress. They're also looking at the potential of being able to stress the rail without cutting it. So you can apply the induction welder. It doesn't need two cut ends. You just put the coils on, heat a section of rail, and then forge it together. So it actually just shortens the rail effectively without ever cutting it, but potentially there an opportunity to carry out stressing slightly different to we would conventionally. And then much the same as we would do once the rail is cooled, it's ground and dressed to achieve the right tolerance and profile on the surface. But yeah, some bits there coming, and hopefully something we can make better use of. It's quite a challenge to get it right, but this is a sort of metallurgical section through it and a hardness test through the weld at the center there. You'd see very little change in hardness, perhaps a slightly improved hardness or increased hardness through the weld section itself up to about 20 millimeters away. A little bit of softening in the heat affected zone, but because the heating is quite rapid and very localized, we can minimize the effects of that overheating perhaps and softening. So from a continuous wear point of view, it's not something that should lead to localized sort of cupping or wear of the weld. It's something where the hardness is maintained through it. So some quite pleasing initial results from the work that we've been doing on there, which I'm hoping, if successful with these are effectively the first site trials. We've seen some very good bench strength, and in some cases the welds have been stronger than, or as strong, effectively achieving a very similar performance to the parent rail. So we've seen effectively the rails bent rather than fracture. And when you actually look at the sort of microstructure, there is very little to see. It, to all intents and purposes, looks like a continuous length of plain rail. So some advantages perhaps there over flashback welding, and there's less risk of getting defects within the fracture face or defects within the weld fusion, because there's less heating and melting at that point. It's a more controlled heating. But that's what testing today is, to produce a number of welds under different conditions, to do the bend testing in a real environment. Currently, it's just been doing short samples in a laboratory, but this is testing now in a real environment under real weld conditions, making sure we get the same. It's quite a tough one, how you deploy it, how you use it. We've got other technology. The aluminothermic welding, not something that's quite as quick. It's not so easy, but very easy to scale. 2 people, a welding team, small van, everything you need, and it will cope with different gaps. Add rail in, so you can stress leaving a gap there and accommodate that. Whereas the flashbang and for induction welding both forge and shorten the rail. This will actually work and increase the length of the rail potentially. So some flexibility there. It's really a challenge. The modern welding processes from Railtech, Pandrel, and Thermic now are significantly improved and more reliable, so less problems with rejected or failed welds. And similarly, the flashback weld, something we've had a number of machines ourselves which we weren't able to effectively utilise. So how do we use the induction welder more effectively? How do we make better use of the equipment? It's great having the technology. We have the flashback welders, but if we don't make any use of them, it's a lot of investment, no returns there. So the flashback welders are being sold on now, the ones we owned. So it's a challenge for any new technology like this. We're trying to replace what is already quite a reliable weld. A couple of the other bits we've been looking at. We did some work with Huddersfield, and we're looking at effectively what was a redesign of our rail. It sounds a bit odd that you go and redesign a rail, but they have done a fair bit of work on it. And it's quite interesting. It's something a bit different. It's not sort of looking at what causes our current problems. Why do we currently change rail? What are the limitations? And the red and green outline there is something they've come up with to say that's a new rail. I think it's been helped by British Steel because it's got quite a lot more steel in it, so it's clearly an interest of the steel manufacturer. But the idea is it offers an ability there within the same envelope, so it still clips down with the same fastening, same foot width, same overall height, but offers some significant improvements both in vertical wear and also increased strength in the foot to reduce any risk of these small cracks causing foot failures. So interesting to see. We're looking in discussions with British Steel about whether this is a sensible way forward. It doesn't present an easy thing. Fish plates don't fit anymore. If you do try fish plates, you've got much less section there to be able to put it. But when you look why we're changing rails, the top 2 pictures are a 60 E2 rail with maximum vertical wear and maximum combination of side wear and vertical wear. Because of fish plate strike risk, we can't have full vertical wear and full side wear, or we run the risk of flanges striking plates and clamps. But using a bigger head in this section, you can see that's with the equivalent 14mm vertical wear. To remain at the same strength, it will go to 28mm of wear. We've got a shorter rail section, but still maintaining effectively a full head profile, a shorter section, and then again combinations of side wear and head wear potentially, where we could see a lot more of the material of the rail used before we then need to change it. And certainly some of the reasons why we're changing things, when you look at broken rails because of foot failures, then they've looked at effectively this strengthened or increased section in the foot to significantly reduce the bending moment, improve the stiffness of the track so that it is better able to take a dynamic loading. So yeah, something a little bit more different. perhaps not something you think of as, and it's not something that's fundamentally changed for well, tens, hundreds of years almost, but something, yeah, we're doing some work with them to try and see what could perhaps be brought in there. A couple of other things. We always talk, and I always talk about record numbers of broken rails. If you look at this for the last 10 years, I'm not sure we can say that. Certainly it's no, we were worse last year than we were the year before. And that's really reflected in the fact we're not fundamentally doing anything different for the last 5, 6, 7 years. So we perhaps don't expect to see any changes or perhaps hope for some changes, but we're really in the lap of gods with the weather. Certainly a very cold winter, we could see probably, I think, 120, 130 breaks. A very mild winter, we might be down in the 90s. But this is one of the challenges going forward, is how do we reduce these further? As I mentioned earlier, we've often done a lot to try and reduce the numbers. But in the last 6 years, we've still had 2 derailments. We had a rail of Glamorgan derailment. We had a derailment at West Sleepburn on a broken switch rail. Unfortunately, with rail, it always tends to fail unsafe. It's very rarely does it fail in a safe way. And certainly with more traffic, increased towage, high speeds, and modern sort of axle counter signalling, where we're perhaps not picking it up to a track circuit, we've got an increased risk of trains continuing to run over broken rails. And as I showed in some of the earlier pictures, certainly a big risk there. If we get a multiple break, then potentially something like Hatfield we could see again. So whilst we've reduced the numbers, the risk is still present. Making sure we run these and do what we can to control that risk is becoming more important. Expectations change dramatically. There's now talk of a 50 by 30 or 50 broken rails by 2030. There's some big expectations to see year-on-year improvement. PPF is looking to focus on performance, so broken and defective rails and certain serious defects becoming a major challenge there, as they're often disruptive to operations if we can't run at line speed. So some big challenges going there. Increased traffic volumes. It'll be interesting to see how the railway recovers post-COVID, what happens and what does the future railway look at. We're certainly perhaps seeing reduced access, challenges to reduce sort of boots on ballast, increased workforce safety. Some of our modern vehicles, perhaps some big improvements in how they behave, but perhaps run more consistently and in some cases perhaps generating more surface damage by running on exactly the same point on the rail, perhaps reducing the wear. But again, something we need to look at and be wary of increased RCF. So some big challenges, still keeps me interested in rail management going forward and looking at sort of how we make those next step changes or incremental changes to improve things. And lastly, it was a big thank you for the opportunity to present and for listening. I hope people found that interesting, and more than happy to try and answer any questions if there's time and people are still interested. Thank you very much.
Hi, Brian. Yeah, certainly very interested. It was a super presentation. We're going to run out of time very shortly, but
yes, apologies,
if there's time, you know, if somebody's got a questions, we could take 1 or 2 questions. So please use the chat. Paul, do you want to come in and ask your question, Polybot?
Yeah, hi, thanks, Stuart. Thanks very much, Brian. Really, really interesting. I'm not an expert at all in this area, but after yesterday's really good PWI conference or seminar about safety, my question is there conflict between using these manual sort of detectors that you showed us and the development of, and the objective to remove track maintenance workers from the track?
I think that's quite a big challenge. I think we've learned that we're becoming more and more reliant on vehicle or train-based inspections. But how do we do that effectively on all of our bits of railway? It's quite easy to put a pedestrian stick through the turnout, crossover and through the S&C, quick and efficient. But to plan a vehicle manoeuvre that covers everything, say in a complex station throw, very challenging. So it's something we are looking at, but I think it's one we've got to face up, that sending people out to do manual inspections in locations is something we've got to look to try and reduce and avoid. Keeping people away from trains is important, but also being able to do something effectively whether it's something with a hybrid type thing, but again, how do we make sure we've got the necessary access to do that, or possessions to run a train backwards and forwards through a set of S&C, for instance? It's quite a challenge to get that sort of level of possession. We see the same with geometry recording. Perhaps we see we've got higher risks in unmeasured or not dynamically measured crossovers, and similar for rail defects. So yes, I think it's a very valid point, something we need to be mindful of. It's easy to write a standard that says go and test this, go and measure the rail depth through the 7 tunnel. You're asking people to go out there and measure it manually, every crib, every sleeper. That's not a practical way of using our staff. It's not a safe way of using our staff. It's not an effective way. We need to find better ways of doing it with either remote monitoring or with things like train-based inspection. Something like S&C, could we fit things which monitor it continuously rather than having to go there as a special and do some testing, but to fit stuff in a static location, we know where there's a problem.
Okay, thanks.
Thank you.
Okay, brilliant. There were a couple more questions, Brian, but unfortunately we've run out of time.
No, apologies for that. I was a bit longer than I thought.
No, I think you gave a great presentation. Certainly, I tried to jot out a few questions, as the presenter go through their slides, and you seem to have answered a lot of mine as you are going through. So it was a very comprehensive.
Yeah, I always struggle whether to a bit of everything or focus on a few things. But yes, it was a bit of a flavour of everything rather than a focus on others. But if people are interested, drop me an email.
Yes, if we could capture the question, then I think that'll be great. And what I can ask Konstantin to do after the meeting is just to send the attendees a note with the answer to the questions, because they are good questions there on the chat. Just to finish then, Brian, on behalf of everybody who attended the call today, thank you very much for your time, and thank you very much for a very interesting presentation.
No, thank you, Gilles. Thank you. I appreciate that. And thank you for the opportunity to present.
Okay, and the last thing, it's nearly Christmas, so I wish everybody a good and safe Christmas, and I will see hopefully all of you in the new year. Okay, bye everybody.
Thanks, Gilles. Thank you, Brian.
Thanks everyone. No, thanks, Sarah. Thanks, Sarah. Thanks, Gilles.
Thank you.
Take care.
Thanks, Brian.
Bye-bye.